Guys, in today's preview, we're going to be talking about Module 4, colligative properties. Let's start with vapor pressure. Vapor pressure is the pressure exerted by a vapor. And as we talked about before, with pure solvents, the weaker the intermolecular forces, the greater the vapor pressure is. In Module 4, we're going to look at how we can affect vapor pressure by adding a solute to a solvent. So specifically, if we add a non-volatile solute, this will lower vapor pressure. And this is for a couple of reasons. One, we're forming new interactions with the solute and the solvent, which keeps those solvent molecules in solution. Additionally, if we actually end up blocking the surface of the liquid, which is going to give us less avenues of escape for our solvent molecules, which again will lower our vapor pressure. I'll write those down. Okay. We are going to determine the vapor pressure of a solution using the following equation. So the vapor pressure of our solution, which is P solution, is equal to the mole fraction of our solvent, whatever solvent we happen to be using, times by the vapor pressure of the solvent. So as we decrease our solvent mole fraction, so at 100% mole fraction, or 100 or 1 as a mole fraction, which means we have all solvent, our solution and solvent would be the same, right? Because it's not actually a solution. But as we decrease this number, we're going to decrease this number. We can also have a volatile solute added. And if you add a volatile solute, as long as it is following Raoult's law, which Raoult's law is going to, this is essentially Raoult's law right here, this equation, being that it is the observed vapor pressure of a solution is the vapor pressure of a solution multiplied by its mole fraction. If we have a volatile solute and volatile solvent following Raoult's law, we get a slightly changed formula. Which is the vapor pressure of the solution is equal to the mole fraction of the first component, which I'm just going to call component A, times by its vapor pressure, plus the mole fraction of the second component times by its mole fraction. So it's essentially a weighted average of the different components of the solution will give you the vapor pressure of the solution. So as a note, a solution that follows Raoult's law This is going to be called a ideal solution. And then, let's make sure, I don't know if I wrote anything. Yeah. And then if it doesn't, follow Raoult's law. I don't know if I'm spelling well. Oh, I am. Sweet. This would be a non-ideal solution. And let me show you what that looks like. So this graph on the left is an ideal solution. And we can see this line at the top. This is our vapor pressure of our solution. And it's going to start out at the same vapor pressure as the A component. And then as you add in the amount of B, you're going to increase until you get up to the vapor pressure of the B component. You can also have deviations. So our non-ideal solutions will either have positive or negative deviations. A positive deviation means that we have a higher vapor pressure than expected. And then a negative deviation means we have a lower than expected vapor pressure. So with a positive deviation, we are going to have a higher vapor pressure, meaning that we have weaker intermolecular forces in the solution than is expected by the solute and the solvent. And then if we have a negative deviation, where our vapor pressure is lower, that means we have greater intermolecular forces than expected. So the sum or the solute-solvent interactions are so strong or stronger than the average between the solute and the solvent individual intermolecular forces. Okay. We also have what are called colligative properties. And technically the changing of vapor pressure, what we're just looking at, I should have specified these were also colligative properties. Colligative properties are essentially the property of the group together solution. And it's looking at deviation from the pure solvent. So for instance, if we have a solute added into a solvent, we're going to decrease vapor pressure. Two volatile solutes added together, we're going to have an average of those two for its vapor pressure. And then we have some other colligative properties that we're going to look at right now. Our first one is boiling point elevation. So this is our boiling point increasing due to adding a solute into a solvent. And this has to do with the fact that we're decreasing our vapor pressure. So if we add a solute into a solvent, when we decrease that vapor pressure at a given temperature, in order to get to boiling, we have to increase our temperature even further to get that vapor pressure up to our atmospheric pressure. So remember that boiling point is the temperature required to get the vapor pressure of a substance equal to the atmospheric pressure. So if by adding a solute in, we're increasing all those interactions, we're decreasing the amount of solute that can leave the solution at any given time, and decreasing our vapor pressure at a given temperature, we have to add in even more energy to get to boiling than we normally would, because atmospheric pressure isn't changing here. We just have to get vapor pressure even higher to meet that at that point. We have an equation that we use. It's delta TB. So this is a change in boiling point. This is not our boiling point. This is a change in boiling point. It's equal to I KB and then a little m. So this this is change in boiling point. This I is our Van Hoff factor. This KB is the boiling point elevation constant. So it's it's going to be specific to a specific solute. And then this little m is molality. So we just learned about molality and using molality, so we're going to be using molality here. The Van Hoff factor I hope I'm spelling that right. I don't really know. The Van Hoff factor is this takes into account our number of particles that are being produced. When dissolving. A solute into a solid. So colligative properties are it's collective, the property of the collective solution. So it's looking at how many particles are in solution when you dissolve. So for a lot of things, that Van Hoff factor is just going to be 1, specifically all molecules. That's because when you dissolve those particles, for every mole of the particles you put in, you get a mole of dissolved particles. For instance, sugar, well, I'm going to do glucose, C6H12O6. When you put that into water, it just becomes C6H12O6 aqueous. So it doesn't break down into more particles. It's the same number of particles as you dissolved. So molecules will always have an I value of 1. Ionic compounds, however, can have an I value greater than 1. So for instance, sodium chloride, when we break or put that into water, it breaks down to sodium ions and chloride ions. So this would have an I equal to 2 because it's breaking down into two particles. So however many ions that our ionic compounds break down into, that is what our I value will equal. Specifically, if this is ideal. Non-ideal, then we would end up with a I value that can be a non-whole number, essentially. Let me show you what I mean by that. Here we go. So here are some Van Hoff values. So we have sodium chloride, and we can see we have different concentrations here. And as we decrease our concentration, our Van Hoff factor, our true Van Hoff factor, or non-ideal Van Hoff factor, gets closer and closer to that ideal value that we would expect. So what actually ends up happening is we have what's called incomplete dissociation, or we're going to be producing ion pairs. And when those ion pairs form, we form a lower than expected Van Hoff factor. So it will decrease with concentration. And I'll specify in a given problem whether we're dealing with a ideal Van Hoff factor, which would be just how many particles it breaks down into, like this, or if we are dealing with ion pairs forming. Again, just show you an image of what I'm talking about. Da, da, da. That's what I mean by an ion pair. Some of the ions are individual ions, so they would be treated like an individual particle, and then some of the ions will be together. That's why we kind of call it incomplete dissociation, because they're not completely dissociating away from each other, or they're forming an ion pair. So this would act as a particle, and then this would act as a particle. So if we have fewer particles breaking down than expected, then we would have a lower than expected Van Hoff factor. And we can actually calculate the amount, or what the I value should actually be, by taking the number of moles of particles in solution. And divide this by the number of moles of solute dissolved. We can also do this as a ratio of And you can also calculate it using the observed colligative property, such as boiling point elevation, over the theoretical. So this would be what we would actually get over what we would get by calculating from our equation, such as our delta TB equals I KB molality. Okay, going back into more colligative properties, we also have freezing point depression. So this is the decreasing of the freezing point. I like to think about colligative properties of just increasing our liquid phase of a solvent. We decrease the freezing point, we increase the boiling point, so we have a lot larger of a liquid phase. So freezing point depression, this is caused, there's, when we start to talk about entropy, I'll bring this back up. But we can kind of just think about it as, because there are these imperfections, these solute particles in this solution, it makes it harder for the solvent to crystallize or to solidify. So you kind of have to decrease the energy of the system further than you would normally to get it to crystallize. Because remember when we're talking about crystallization or solidification, this is a ordered arrangement of those particles into that crystalline solid. So if we have these imperfections in the way, we kind of have to slow down everything even further to make that crystalline solid. So that added disorder makes it so that we need a lower temperature to freeze. Our equation for this is our delta Tf. So our change in our freezing point is equal to negative I Kf molal. So this is negative because it is a decrease in our freezing point. And again, this is our change in our freezing point. This is our Van Hoff factor right here. This is our freezing point depression constant, which will be based on whatever solvent you're dealing with. And then this is the molality of our solute. Okay. Whatever. Boiling point elevation, freezing point depression. We can also look at osmotic pressure. So real quick, osmotic pressure. This is the amount of pressure that must be applied to stop osmosis from occurring. And in case you have forgotten what osmosis is, or you've never learned what osmosis is, when we're talking about osmosis, this is the movement of solvent particles across the semipermeable membrane. So a membrane that would only really allow solvent particles to cross, not usually solute particles, they're usually a little too big. So across a semipermeable membrane, from low solute concentration to high. So the solute is going to move towards the side with more, sorry, the solvent is going to move towards the side with more solute particles to try and equalize the concentrations of our solute particles. So it's kind of an image of what's going on. I really like images. This is osmosis. So we have the pink stuff is our solvent. The purple balls are our solute. And we're going to move the solvent particles across the semipermeable membrane until the concentrations of both sides are the same. So with osmotic pressure, we are preventing that from happening. So I usually kind of think about it in terms of applying a pressure. So I usually think about a U-tube. So the solvent will go across the semipermeable membrane. moving towards the side with more solute particles. And then osmotic pressure is that pressure that can be exerted to stop osmosis from continuing to occur. Please note that osmotic pressure is going to increase with amount of solute particles. Which is why it's a colligative property. We can solve for osmotic pressure, which is given as an uppercase pi. It's going to be equal to our Van Hoff factor times by our molarity of our solution times by our gas constant R. Specifically, this is going to be the gas constant that's going to include pressure. So 0.08206 liters times by atmospheres over moles times by mole times by Kelvin, because this is a pressure, right? Which will be in atmospheres. And then times by our temperature, which will be in Kelvin. So we can see that not only the concentration, but the number of particles will affect our osmotic pressure, just like it does our other colligative properties. Okay. We can have something called reverse osmosis. So this is causing solute particles, or sorry, solvent particles to go in the opposite direction. And we can get this by applying a pressure greater than the osmotic pressure. And you've probably, if you've ever had a Dasani bottle of water or some other bottles of water, it says that they're purified by reverse osmosis. So they're literally just taking dirty water and they're shoving across just the water particles, and leaving behind all the solute particles to purify that. So other terms that you should know the term isotonic. So these are solution terms specifically. We have an isotonic solution. We have a hypertonic solution. And we have a hypotonic solution. Again, most people probably already know these terms. These are definitely biology terms. And most everyone in this class is a biology major. So isotonic means it has the same osmotic pressure as a red blood cell. Or as whatever we're comparing it to, I guess we say. But generally, we're comparing it to a red blood cell. But we can just talk about two solutions being isotonic within each other, which means they have the same osmotic pressure. If we are talking about hypertonic, the concentration of that solution is greater the concentration of the solute in that solution is greater than whatever we're comparing it to. And osmotic pressure. Again, then another solution or a red blood cell. And then hypotonic is our concentration of solute and osmotic pressure is lower. So in terms of those solutions with red blood cells, if we have if we have red blood cells in a isotonic solution, the flow of water in will be equal to the flow of water out. If we have red blood cells in a hypertonic solution, the water will leave the cells in order to try and get more concentration outside of the cell to equalize the concentrations. And then if we have red blood cells within a hypotonic solution, then we are going to get more water going into the cell than leaving the cell. In the case of a hypertonic solution, we can get crenation. Really kind of shrink up, and hypotonic, we can get lysis, hemolysis, breaking of those cells, or bursting of those cells because of how much water is being flooded into those cells. I think those are the important things for this. We've already talked about the Tyndall effect and colloids. So I think that's everything for this module. There's a lot of calculations in here, but other than that, not a lot of content. I'll see you guys soon. Have a great day. And bye.